Bueno, chicos, ya son las 8:35, entonces ya empezaremos, ¿no? Si bien recuerdan, la última clase que tuvimos en CCM, pues vimos parte de reacción química, ya habíamos hecho una actividad de reacción química y luego vimos parte de la presentación. La presentación, si recuerdan, ya está en Blackboard y entonces ahí la pueden ver, ¿no? Entonces hoy vamos a continuar con reacción química, pero ya entrando a cosas específicas que tienen que ver con balance de materia. Y acabo de recordar que esta clase es en inglés, jajaja. Entonces disfruten ustedes el cambio de idioma. Okay, so we have to see now how to work with chemical reactions in mass balance process. Okay, so what we're going to do is to start the presentation, and I will do some comments about it and so on. Please remember that in the participants pane on Zoom, you can raise your hand, or you can do non-verbal communications like go faster or go slower. Okay, so use that tool to inform me if you need something. Okay, if you raise your hand, I can mute your microphone so you can ask the question, and everybody is going to hear it. Okay, so without further notice, we go to the presentation, and we'll start to see where were we. Okay, let's see. Okay, so this was the last slide that we saw. Okay, it was about the Haber process to produce ammonia, and we saw about the reactor and the conditions and so on, right? So it's very important to know what is the conditions in each reaction and how to proceed with those values. Okay, so now we're going to see how to calculate the degrees of freedom in a process with a chemical reactor. If you remember, in mass balance without chemical reaction, you only had the unknown variables and the equations that you could have, and that was more or less the degrees of freedom, right? But in chemical reaction, we have three different ways of calculating the degrees of freedom. Okay, so we will see those three in this class. Okay, so the first thing to know is what is an independent equation. Okay, so for example, we have here two different equations, right? Number one and number two, right? So are these two equations independent? Is there any mathematical equation that we can do to one of them to have the other one? In this case, yes, right? For example, if we have this one and we multiply it by 3, you're going to have the second one, right? Doing this, right? So these are not independent equations, of course, okay? Because we can arrive to the other one doing a simple mathematical equation like a multiplication or a division, okay? So, for example, in this case, what do you think? Are these three independent or not independent? Try to work it out for a couple of seconds and we will see if they are independent or not. Is there anything we can do to this equation or this one or to adding these two equations or what, right? That's the whole point. So, did you arrive to anything? Any result? Okay, these three equations are not independent because this one, the third one, you can obtain it through multiplying the first one by 2 and subtracting the last one, right? So this one would be 2x plus 4y equal to 8, right? And if we subtract the last one, 2x minus c, sorry, that was the c minus c, is equal to 2, right? So if we do that, the 2x cancel, so this is 4y. We change the sign because we have a minus and a minus, so it's plus c, and this is 8 minus 2, right? And it's equal to 6. Okay, so you see that these three equations are not independent. Okay, that will be the case in some chemical reactions. It's more or less the same thing. If we have three different chemical reactions and they can produce the one of those, then they are not independent, right? Okay. So another thing is the independent species in the problem or in the process. Okay. In this case, I'm going to read the description. It says that if two molecular species are in the same radio, like air, for example, to each other, wherever they appear in a process, and this radial is incorporated in the flowchart labeling, balance on those species will not be independent equations, okay? Because they keep the same radial, so they have the same properties, so they don't change between the inlet and the outlet. Similarly, if two atomic species, like for example carbon, hydrogen, oxygen, the components of the different compounds, well, if the atomic species are in the same radio, wherever they appear in a process, balance on those species will not be independent equations. Okay, so how can we see that? For example, in this particular process, we have an inlet here that has oxygen and nitrogen. And if you see, you have a relation between them. 3.76 times the number of moles of oxygen is the number of moles of nitrogen, right? And then you have another inlet that is tetrachlorine carbon, and the outlet we have a number of moles of oxygen, N3, and we have a relation for nitrogen as 3.76 the number of moles of oxygen, right? So if you see in this case, this particular process absorbs the oxygen and the nitrogen, absorbs the CCl4, right? And you have in one of the outlets, you have the CCl4 that goes into vapor with the oxygen and nitrogen. But the important part here is that oxygen and nitrogen are kept in the same relation, right? 1 to 3.76 moles of the nitrogen. So in this case, oxygen and nitrogen are not independent, right? Because you can obtain one through the other, right? A second. Okay, so I hope that is quite clear. So now the species are not are in the same proportion. So in the inlet and the outlet, and they don't behave independently, right? And that is why many times to these two we assign just air, right? Because they keep the same proportion, and as the proportion doesn't change, the mass doesn't change, so you can use it as just air. Okay. Okay. So now how we calculate the degrees of freedom? We have three different ways of doing it. We have molecular species balances that have to be with the molecules of the components of the compounds. Okay, we have the atomic species balances that have to be with the atoms: carbon, hydrogen, oxygen, fluorine, so on and so forth, chlorine, etc., etc. And we have the extent of the reaction. Okay, so let me go through each one of them. Okay, so to calculate the degrees of freedom of the molecular species, we have the number of non-labeled variables. Okay, so let's say that it's a flow, or let's say that it's a fraction, a molar fraction, or so on, right? Then we add the number of independent chemical reactions. Okay, so we have to make sure that the chemical reactions are independent, and then to see how many are there. Okay, and then we subtract the number of independent molecular species balances. Let's say the number of different components that we have. Okay, so oxygen, methane, carbon, CO2, and so on and so forth, right? And then we subtract the number of other equations related to non-variables, right? This is extra equations that we have that relate more, well, the components, right? And that will give us the number of degrees of freedom using molecular species. Okay, so if we do atomic species balances, we have, again, the number of known variables first. Then we subtract the number of independent atomic species balances. So the atoms that make the matter, let's say carbon, hydrogen, oxygen, right? The different species. And then, we do the we subtract the number of molecular balances of independent or non-reactive species. If you remember, some problems that we did in class were about an inert gas, right? An inert gas doesn't react, so we could count it here, right? In non-reactive species, right? And then we subtract the number of other equations relating to known variables. Again, additional equations that relate the known variables in the reactor, and that gives us, again, the number of degrees of freedom. And the last way of doing is the extent of the reaction. In the extent of the reaction, if you remember, we have one extent of the reaction for each particular reaction. So again, the number of known variables, then we add the number of independent reactions, as in the molecular species balances, and then we subtract the number of independent reactive species, so the molecules that react, right? And then we subtract the number of independent non-reactive species, or, for example, inert gas, nitrogen, if we're using the air for the oxygen, and so on. And again, we subtract a number of other equations related to non-variables, right? So that's how we do it. Okay, so now let me see, we have, okay, so we're going to do a quick example, okay? In this reactor over here, here we have a reaction, well, a reactor that goes C2H6, right? So I'm going to write down the chemical equation, C2H6, right? And if you see, that's the only reactant, right? Or only reagent. So that particular reagent is going to decompose in these two, in C2H4 and hydrogen, right? So we're going to have the decomposition of this one into C2H4 and hydrogen. That particular reaction, it's already balanced, right? We have two carbons, 6 hydrogens, 4 and 2 hydrogens, and 2 hydrogen, right? So 6 hydrogens in each side. So this one is balanced already, right? So let's obtain the degrees of freedom for each case, for the molecular species, for the atomic species, and for the extent of the reaction. Okay, so the number of known variables. If you see the diagram that we only have as a known variable, we have N1 and N2, right? So we have two variables, that is N1 and it's N2, right? Number of independent chemical reactions. We have one chemical reaction, that's it. And then we have to subtract the number of independent molecular species balances, right? Molecular species, we have one molecular species, that is the C2H6, then we have C2H4 and hydrogen. So we have three different molecules, so we have here 3, right? That is the C2H6, C2H4, and hydrogen, okay? And then a number of other equations related to known variables, we don't have any of those, so 0, right? So we have 2 plus 1, 3 minus 3, 0 degrees of freedom. That tells us that using the molecular species balances, we can solve this particular problem without anything else, right? We have enough information to solve that problem. So now with the atomic species balances, okay? So we have number of known variables, again, 2, that is N1, and it's N2. Then we have number of independent atomic species balances. So the atoms that make this compound. So we have carbon and hydrogen, carbon and hydrogen, carbon and hydrogen. Okay, so we only have 2, carbon and hydrogen, right? Number of molecular balances of independent or non-reactive species, we don't have any of those, so 0. And number of other equations, we don't have those, so 0. Okay, we have 2 known variables, and we have 2 independent atomic balances, so we have 0 degrees of freedom. Okay,
Professor,
yeah.
An equation, molecular balance on independent non-reactive species would be when species enters and doesn't react with anything, or what do you mean with molecular balance?
Yeah, when you have some number of independent molecular species balances, is the molecules that are in the reaction. So in this case, those three, right? C2H6, C2H4, and hydrogen, right? But in the atomic species, you have independent non-reactive species. For example, if you're using air for the oxygen and not for the nitrogen, nitrogen is not going to react. So nitrogen would be an independent non-reactive species. Right?
Okay, thank you.
Welcome. So the last one is the extent of the reaction. So again, number of known variables, 2 again, the same 2, N1 and N2. Then number of independent reactions, we will have 1 reaction, and of course it's independent, so 1. Number of independent reactive species, we have 3, right? Again, C2H6, C2H4, and hydrogen, so 3. Number of the independent non-reactive species, again, we don't have those in this particular problem, so 0. And number of other equation relating non-variables, 0 again, right? And that gives us 2 plus 1 minus 3, 0. Okay, so this particular problem can be solved with either of the balances, right? With molecular, atomic, or extent of the reaction. But that is not the case always. Okay, some particular problems can be solved only using one of the methods. Okay, so now we know that we can solve this particular problem. That it's a very easy problem. Of course, it's just an introduction. With any of the balances. Okay, so now we're going to solve them. Okay, so I'm going to change to another software so we can do that. Just give me a second. If I'm going to upload the presentation. The presentation is already on Blackboard in materials, in presentations. That's it. Okay, so now we go to this software that is called Blue. We're going to solve this problem. Okay, so let's see. Yeah. So we had this problem, a reactor. Here we have 100 kilomole of C2H6. Here we have 40 moles, 40 kilomoles of hydrogen, of H2. Just let me remind. Let me remind which one was N1 and what was the and 1 was the amount of C2H6 that remained in the system, and N2 was the amount of C2H4 that was produced or was decomposed, right? Okay, so we're going to solve the problem with the 3 different methods. Okay, so the first one is the molecular species, right? Molecular species, right? Okay, so in this particular way of solving a problem, what you have to pay attention is what happens to each of the components. Okay, so for example, if we do hydrogen balance, we have to pay attention to what is going on. For example, we don't have hydrogen at the inlet, right? We only have hydrogen that is produced in the reaction, right? So the outlet is going to be equal to the generation of hydrogen in this case, right? We don't have any other kind of thing, right? So we know, well, in this case, particular case, we already know that hydrogen is going to be 40 kilomoles, right? So the outlet, it's going to be the one that was generated, and the one that the hydrogen that was generated was the 40 kilomole, right? So pretty straightforward. And then we do a balance for the other two, for C2H6 balance. Let's see what happens, right? So in this case, we have an inlet of it, right? So we have part of it that goes into the system, okay? And we have some of it that goes out because we have an N1 term, and we have part of the consumption, right? So part of it, part of the C2H6 was were reacted and decomposed into the other two products, right? So the inlet or the input is going to be equal to the output plus whatever was consumed, right? Okay, so to solve this, the input, we know the input, we have 100 kilomoles of it, right? The output is exactly what we want to find, that it's N1 with a dot, plus what it was consumed. So what it was consumed, we can calculate it, the amount of hydrogen that was produced using the stoichiometry of the reaction. Okay, so we had 40 moles, 40 kilomoles of H2, and then we have to look for the stoichiometric relation that, if you remember, was C2H6 that decomposed into C2H4 plus hydrogen, right? So the stoichiometric coefficient is 1 to 1. So we put that into our relation, right? For each kilomole of H2, we have 1 kilomole of C2H6. Okay, so we cancel units over here, and then we obtain, well, the equation that is N1 with a dot is going to be equal to 100 minus 40, that is 60 kilomole, right? So far, so good. And that is the C2H6 balance. The only one that we're missing is the C2H4, okay? So doing a balance like this one, a molecular balance, is more or less the way we do it in chemistry, right? For example, in your chemistry class, in your theoretical chemistry class, you did balances like this one, doing relations. Let me put a color. Doing relations like this one over here, like this one over here, to have to obtain what was the amount of it, right? Okay, so now we have to do, lastly, we have to do the C2H4 balance, right? And again, we have to write an equation like this one, the input and the output. But in this case, we only have the output, right? So what was generated, the generation of it, it's equal to the output. Okay, so how we calculate the generation? The generation we calculated through something similar to this, right? Okay, so the output is N2 with a dot. It's equal to the generation. So the generation, we know that we have 40 kilomoles of hydrogen. And again, the relation for each 1 kilomole of hydrogen, we have 1 kilomole of C2H4. And N2 is equal to 40 kilomole of C2H4, right? So there we have our answer, right? We have the first unknown variable was this 40 kilomoles of C2H4, and the other variable was this 60 kilomole of C2H6, right? Okay, so please let me know if you have any questions. Raise your hand in the well, or you can unmute your own microphone to ask a question, like Marco did a couple of minutes ago. So anybody has a question about this particular method that we did here? That is the molecular species.
Professor?
Yes.
Why would the C2H6 balance, the 40 kilomoles of hydrogen, are considered as consumed?
Because you know, in a reaction, if you have a reaction they're going to behave with the stoichiometry of the reaction, right? So you know, because the problem gives you that information that you have 40 kilomoles again, right? At the end, you know that 40 kilomoles was produced, right? So if 40 moles was produced, then it means that the other, wait a second, and it means that 40 kilomoles were produced. So those have to be in relation with the stoichiometry of the reaction, right? So 1 to 1 to 1, right? So if you produce 40 kilomoles of hydrogen, it means that those 4 kilomoles of hydrogen comes from 40 kilomoles of C2H6 that reacted, right? Make sense?
Yes, thank you.
Okay. I have a question here in the chat, so let me address that one. Teacher, in the H2 balance in the same generation and out. Yes, that's what well, the out is equal to the generation. Yes, in that case, right? We know this information already, right? We have it on the problem, right? 40 kilomoles of hydrogen. Yeah, but that one is generation is equal to the outlet, right? Any other questions, guys?
Teacher, why we don't consider the input in the first one and last one?
Well, in the first one, in hydrogen, we don't have an inlet, we don't have an input, right? We don't have here in the declaration of the problem, we don't have any hydrogen that goes into the system, right? The hydrogen is going to be only the hydrogen produced in the decomposition, right? And again, in the case of the C2H4, we don't have any C2H4 at the beginning of the process. We don't have an inlet for it, right? Just an output of it. Yes. Any other questions, guys, about this particular? Okay. Let me remute everybody because I'm trying to hear a lot of noise here. Wait a second. Okay. So now we're going to do the second method, that is the atomic species, right? I'm going to make a new page. Again, right, we have our process, a lousy drawing. So 40 kilomoles of hydrogen, and 1 for the C2H6, and 2 for the C2H4. Here we have 100 kilomole of C2H6. And the reaction is just a decomposition. Okay, there we have it, right? So now, in atomic species, the only thing we pay attention to is the balance of the atomic species, right? In this case, carbon and hydrogen, right? So we're going to have carbon balance and a hydrogen balance. Okay, so the carbon balance is, well, the inlet is equal to the outlet, right? The input, it has to be equal to the output, right? Because matter is conserved, right? So in the input we have 100 kilomoles of C2H6, right? And we need to calculate the amount of moles of carbon in this case, right? So we have to do the relation. For each kilomole of C2H6, we have 2 kilomoles of carbon, right? And that has to be equal to the amount of carbon in the outlet, right? Hydrogen, of course, doesn't have any carbon, so the carbon is in the C2H6 and the C2H4, right? So the amount of carbon that you can find in those is N1, that is the number of moles of C2H6, and again, the relation one, right? 1 kilomole of C2H6 has 2 moles or 2 kilomoles of carbon. And the other one, the C2H4, again, we have N2, and again, the same relation. For each 1 kilomole of C2H4, we have 2 kilomoles of carbon, right? Everybody agrees on that? Okay, and we can do the hydrogen balance too, right? So the hydrogen balance is the same thing, is the input. It's equal to the output. So in the input we have 1 kilomole of C2H6, and this time around the relation is for each kilomole of C2H6 we have 6 kilomoles of hydrogen, right? Because we have this 6 over here. And in the output, well, it's going to be the same thing, right? We have, in this case, we have 40 kilomoles of hydrogen, right? And 1 kilomole of H2 has 2 kilomoles of the hydrogen atom, right? And then we have to add the number of moles that we have of in C2H6 that we have for each kilomole of C2H6. We have 6 kilomoles of hydrogen, and in the H4, in the C2H4, we have for each kilomole of C2H4, we have 4 kilomole of hydrogen, right? So we have two equations. Let me grab another color. We have two equations. We have equation 1 and equation 2. And we have two variables, right? N1 and N2 in each of the equations, right? So if you solve these particular equations, you're going to find the same thing as we did with the last problem, that N1 is equal to 40 kilomoles. And what's this? Let me check. Yeah, N1 was 60 kilomoles. So let me erase this one. So it was 60 kilomoles of C2H6, and N2 was 40 kilomoles of C2H4. Okay, so with the equation that we write, that we wrote here, the equation 1 and equation 2, solve the problem. Okay, take 2 minutes to solve it, to do the algebra, to see if everything is the same as it should, and then we continue. Okay, if you have any questions, please raise your hand, or either unmute your microphone and ask the question directly, right? Let me know if you have any doubts.
Prof,
See?
how we will know which method to use in each problem? Because it's They are
Okay.
like three methods, like, right?
Yeah, the three different methods. I'm going to see some considerations after we finish solving this particular problem. I'm going to see some considerations to choose each one. But you can do either one, the one that you prefer or the one that is easier. For example,
The
there
first
are
one is easier, right?
depends on the particular system, because for example, if you have many reactions and all those reactions are of hydrocarbons, well, you only have carbon and hydrogen and probably oxygen, right? So you don't have three different atoms. So and maybe you need, I don't know, you have 10 different reactions, right? So it could be easier to do it through atomic species instead of doing it through molecular species, because molecular species can have, let's say, 50 different molecular species, but atomic species you only have three. So it's easier in that way.
So when we have less reactions, we use atomic species, and we have
Well,
a small reaction, we use molecular species.
yeah, if you have only a few couple of molecules, you can use molecular balance and it's fine. But many times it's easier to do it with atomic. And if you're going to use, for example, an Excel table, it's easier to do the extent of the reaction. That is the last one that we're going to see.
Okay.
So it depends. Yep.
Changing.
Okay, so did you solve it already? Raise your hand if you solved it, please. Or say yes in the participants pane in the Zoom, please.
Teacher,
Yes.
in the addition, we consider N1 and N2 units as C over C2H6.
Well, you're going to cancel those units, right? Well, no, the units in N1, it's kilomole of C2H6, yes, and in the N2 it's C2H4, kilomoles of C2H4, yes.
Okay.
Yeah, that's why you have to do this kind of relations, right? To cancel those particular units, right?
Okay.
So any questions on this particular? I only have one hand that says that finished. Everybody else? Carlos Solis 2, Alonso Stone, Marco 2, Emiliano, and Marco. Alonso 2, Alejandro. Okay, so we will continue, okay, through the last method. The last method, as I said in one of the questions, it's easier to program for it. For example, in Excel, if you need to solve a big problem and you're going to use an Excel spreadsheet, I'm going to make a video about it. You can use this particular method, the extend method, the extend of the reaction method. Okay. So let me check again another page. While everybody finish. Let me do the same thing as the time. Okay, so if you remember the definition of the extent of the reaction, we only have one extent for a particular reaction, right? So what we need to do is to write the equations for each of the atoms, right? For example, in this case, the number of moles of C2H6 at the output, right? Is going to be equal to the number of moles of C2H6 at the inlet, and this is minus the coefficient, the chemical coefficient, that is 1 in this case, times the extent of that reaction, right? And that for each one, right? In this case, for example, for the number of moles of hydrogen at the end will be the number of moles of hydrogen at the beginning, right? And in this case, plus, because it's a product, so it's going to be produced, the stoichiometric coefficient 1 and the extent of the reaction, right? And the same thing for C2H4, right? We have the number of moles at the outlet, it's going to be the number of moles at the inlet, plus 1 time the extent of the reaction, right? Those are the equations. Those are the equations that we have. And then we need to, well, to substitute the values that we do know, right? For example, in hydrogen, we know that we don't have any hydrogen at the beginning, right? So we cross that. Let me grab an isocology to go. So this term, we don't have it, right? We don't have hydrogen at the beginning, and we don't have C2H4 at the beginning, right? Okay, so in this particular case, in hydrogen, we know that the final number of moles of hydrogen are 40, right? We have it on the diagram here, 40 kilomoles, right? And that has to be equal, well, to the extent of the reaction, right? So now we have the extent of the reaction. The extent of the reaction is 40 kilomoles. And then the only thing we have to do is to substitute in the other equations. For example, for C2H6, we know the final number of moles. That's what we want to find. So N1, right, it's going to be equal to the number of moles at the beginning, that is 100, minus, right, 1 time the extent of the reaction. And 1 time the extent of the reaction, it's 40. So we have at the end 60 kilomoles, right, of C2H6. And in the case of C2H4, we want to know the number of final number of moles of C2H4, that is the N2, and this is going to be equal to, well, only the extent of the reaction. That the extent of the reaction is 40 kilomoles of of C2H4, right? So obviously we found the same result as in the other two methods. It's what we expected to find, right? And that's it. Those are the three different methods that we have. Let's see if I have something. Okay. Any questions or anything? So this particular method, if you see, it's pretty easy for only one reaction, right? We only have one extent of the reaction. But if you remember, we solved a problem, well, a problem with two different reactions, and then you have, well, two different extent of the reaction, right? One extent of the reaction 1 for the chemical reaction 1, and extent of the reaction 2 for the chemical reaction 2, right? So it depends on the number of equations and the of chemical reactions. It's easier or not to use the extent of the reaction, right? Okay, so do you have any questions about this method?
Prof,
Yes.
why did you cross the NH2? They say NH2 equals to something I don't.
This is the, well, okay, sorry. This is the extent of the reaction, right? This particular letter that I can write very good, that is the extent of the reaction, right? I crossed this number of moles in this case of hydrogen and in case of the C2H4 because those are the number of moles at the inlet, okay? at the beginning of the reaction. And we don't have any of those, right, in this particular case. So we don't have those moles, so we cross them. Those are 0, right? 0 moles at the beginning and 0 moles at the beginning for H2 and for C2H4, right? So we don't have any amount of those compounds at the beginning of the reaction. That's why they only change to the extent of the reaction. In this case, with the hydrogen, with the information of the hydrogen, the 40 moles of hydrogen at the end, we know that the extent of the reaction then it's 42, right?
Okay.
Yep. Any other questions, guys? Everything fine?
About the second method, we had to do a system of equations.
Yeah, well, yeah. Sometimes, many times, what you find is a system of equations. Depends on the coefficients that you have and the information that you have. But yeah, most of the time you find a system of linear equations, right?
Okay.
Depends on the amount of course, of atomic balances that you have, right? In this case, only carbon and hydrogen, but in many reactions you have plenty more, right?
Thank you.
Any other questions, guys? No. Okay, so then we're going to change again to the presentation to see a couple of things. That's it, right? Okay, so this. Okay, so we solved already, and okay, so some considerations, right, for the different methods. The atomic species balances generally leads to the most straightforward solution procedure because you only have to make one equation for each atomic species, right? Especially when more than one reaction is involved. As I told you when we were solving that problem, if you have, for example, 20 different chemical reactions, well, and you only have 3 different atomic species, it's generally easier to do it that way, right? The extent of the reaction are convenient for chemical equilibrium problems and when equation solving software is to be used. For example, in the case of Excel, if you want to use that, or if you have any other software, even in your calculator, right? And the molecular species balances require more complex calculations than either of the other 2 approaches and should be used only for simple systems involving one reaction. So yes, for the easiest 2, well, it's the atomic and the extent of the reaction, right? For example, for me, that I'm a chemical engineer, the molecular species balance is it's pretty logical for me, at least, right? Because I've done it many times. But if you're not very used to the molecular species balance, the atomic and the extent of the reaction are pretty good and pretty straightforward, right? Okay, so this week what we're going to do is a couple of activities. One such activity is to do the first part of the project. Okay, the first stage. So I'm going to open this document. You have this document already on Blackboard too. Okay, so it says that the final project of mass balance class will consist of a study of an industrial process and the modifications that can be made to improve it. The project will be done in teams of 4 people and consists of 3 stages. The project must be a balance in an industrial process of your interest that has at least 10 production units that include mixers, recyclers, purge, mixing points, and so on, right? Distillation, crystallization, and so on. And at least 1 reactor, okay? If you don't have 1 reactor, I'm not going to accept that particular project, okay? So the first stage or first delivery, what you have to send before Thursday is to choose the process, any process that you want, but that is interesting to you, okay? Justify the selection of that particular process. We choose this process because we are IPTs and we think that it's going to be good for our career because we're going to learn about this particular process, right? Or anything else. And you need to deliver the process diagrams that, well, it tells me that you pay attention to the 10 operation units and the 1 reactor, right? You can do the teams as well, whatever you want, the way you want. And then the second delivery is going to be the preliminary calculations. Okay, so for example, let's say that you choose a process that doesn't have a recycle, right? And you want to see if that recycle it's better for the process or not. Okay, so the preliminary calculations could be, for example, the calculations without the recycle, or the preliminary calculations for the reactor, or the preliminary calculations, well, more or less whatever you want to show me that you have doubts if it's going to be correct or not. Okay, and in that particular delivery, in the second delivery, you need to have a proposal of the optimization analysis. So let's say that you want to do a recycle. Well, we're going to do a recycle in this particular operation, so we can put it again through the reactor and to obtain a more efficient process and so on, right? And the final delivery, well, it's a document that has this structure and those points assigned to each part. So an abstract, it's a resume, what you did, why you did it, what you found, and what are the main conclusions. That's more or less an abstract. If you go to any scientific journal, read a couple of abstracts, and you're going to see that that's more or less what they say, right? We did this because of whatever reason, and we find a couple of the best results, or the more important results, and that means that the conclusion, right? The problem discussion is, well, more or less the first delivery, right? Why would you choose the process? Why you could justify, how you justify it, and so on. The introduction, well, it's a part of any document. What is the background of that particular process, for example? Well, we choose the beer process because beer is one of the the greatest industries in Mexico, and so on and so forth, whatever you want to. The process diagram is the one that you're going to deliver, right? You have to deliver two process diagrams, right? One without the optimization, and one with optimization. Then the table of initial variables. The table of initial variables is very important because if you don't have enough variables, right? Compositions, temperature, pressures, so on and so forth, you can't solve that problem, right? So you need that initial variable. Considerations could be that, for example, you didn't find the efficiency of the reactor, for example, right? Of the yield of the reaction. So you can say, okay, we consider that the yield of the reaction was 75% per stage. Okay, that's one consideration, right? Or we consider that the separator or the splitter was 50% and so on. If you don't have that particular information from your research, you can do a couple of considerations, right? The calculations that you can add an Excel, for example, or you can add an appendix with all the calculations of all the streams that you needed to calculate, right? Then the final table is the huge table of, well, depends on the amount of streams, of course, but the table with each stream and the components that go in that particular stream, and either the molar fraction or the mass fraction, right? And the mass of each stream. Then analysis on how to improve the process. Well, you said, okay, we wanted to do a recycle, so we found that the process is 70% better or not, or whatever you found, right? That's the analysis, exactly. Then an economic analysis. You only have to put the raw material and the products. So you say, okay, we started with 1,000 kilograms of methane and 300 kilograms of blah blah blah, and those material costs some amount of money, and those products we can sell it at this amount of money. So the gain or the profit in that particular process is blah blah blah, right? And last is the conclusion. The conclusion is it's not if you work correctly or not. It's if what you found, right? We found that the optimization was correct, or the consideration that we did, they were not on point because whatever reason that you found, right? That's part of it. And then the last point is the reference that you have. Of course, you have to use citation through the text, right? Either method that you want to use is fine. APA is one of the most consistent and more used, but you can use either one. It doesn't matter, right? And some some points about the report. Should be maximum 7 pages. Well, the Excel can have any information that you want, of course, of calculations, but the document that you deliver has to be 7 pages maximum in Arial 11, single space, and margins of 1.5 centimeters, right? So it's more or less the same amount of information for each project. Okay, so this is the document. You have this document already on Blackboard. So the first delivery, this one over here, yeah, this one, first delivery, it's for this Thursday before the class, before 8:30, right? The assignment space in Blackboard is already there, so you can upload it anytime you want before Thursday at 8:30. You can do the teams whatever you like, however you like. And the other activity that we're going to do, that you can do it individually or in teams of 2, for example, in couples, if these chemical reaction problems. Okay, so this we have 2 different problems, right? We have 2 problems, and so you have to solve them before Thursday at 8:30. And at that time, I'm going to upload at YouTube a video showing how to solve those particular problems. And a last one that I have here that I couldn't do in this particular session, because in theory we should only assign 1 hour to this kind of interaction. Okay, so you need to solve these 2 problems. You need to solve these 2 problems before the class, and so you upload it to Blackboard, and then at 8:30 I'm going to upload the video to YouTube, so you can watch how you should solve that particular problem. Okay, in the first one you have 4 parallel reactions. Okay, and in the second one you have 2 parallel reactions. Okay, these are not the most complex problems, but well, you need to think about how to solve them. Well, what is going to be the easiest way to solve those particular problems? Okay, so those 2 activities for this week, right? And then on Thursday I'm going to assign you an activity about combustion. That is the next topic. Okay. Also I upload the second homework. The second homework is for the second partial. It has 20 mandatory problems and 2. No, sorry. I don't know what. I don't remember if it was 20 or 23 problems. It's in teams of 4. You can rearrange the teams. It doesn't matter as long as you deliver it. And it's going to be, you have to deliver those. Well, I'm going to sign the date, but it should be for the first part. Well, for the exam, right? The exam is going to be presential. I'm going to ask for a classroom. I don't know if they're going to give it around here in, for example, Colegio Madrid or the UPM or whatever. Okay, but I will let you know in time. Okay. So that's it for this class. I don't know if you have any questions, any comments, or anything else that you need to address.
Professor, where can we find those chemical reaction problems?
There should be in Blackboard, in materials and, sorry, no, in activities. The chemical reaction problems is in activities.
Thank you.
And the homework is in materiales and tareas, and the project is in the project folder that it's in.
And it's all for Thursday?
The chemical reaction problems, yes. The project, those 2, yes. The homework is for the exam, for the day of the exam.
Okay.
Yep. Any other questions, guys? Emiliano Castro, Emiliano, what Castro?
No, Marco already answered. Well, you already answered my question that Marco asked.
Okay, very good.
So it's okay.
Okay, anybody else, guys?
If we have a doubt, we can text you for Zoom.
Yeah, well, you can send me an email, for example, if we are not in the advice sessions, but remember that we have, well, I'm going to be connected at through Zoom on Wednesday and on Thursday, right? You have the you have the schedule on the syllabus update in Blackboard. So I'm going to be here in Zoom. So if you have any questions, log in and we can see it. Right?
Okay. And can we have a presential class?
Well, not soon. Well, if okay, for example, if more than 50% of the group needs a presential class, we can arrange it. But if you have particular, for example, if you need an advice session in person, well, we can arrange that too. Or in small groups, for example, we can gather in the Starbucks coffee here in CCM or something like that.
Oh, okay.
But
Yeah.
that we can arrange it through email once.
Thank you.
Anybody else, guys? Okay, so we'll see. We're going to have the next session on Zoom is going to be next week on Monday again. Okay, so if you have any questions, remember my sessions. I have my email. So here I am for anything that you need, of course, right? Okay, so see you on Monday, and well, remember the activities that you need to deliver on Thursday, please. Okay, see you guys.